Okay, this is lesson 14 of module 7. We've been talking about the decimal expansion of rational numbers and irrational numbers. And so in this lesson, we're going to work on the decimal expansion of pi. So pi is an irrational number, we've been told. I didn't have this font on my computer, but we use a Greek letter pi for this number, and most of us are familiar with it. So let's look at how pi is used. So in this first exercise, you're asked to write an equation for the area A of the circle shown. So we could say that the area is equal to, and I would encourage you to pause and do this yourself, or maybe you have it done while I'm chatting here. But remember, the area formula for a circle is pi times the radius, which in this case is 6.3 centimeters, the radius squared. Pi times the radius squared. So if we kind of write this in a more general way, we've got pi times 6.3 squared times our units, which is centimeters squared. That exponent's going to work on everything that's in the parentheses there. Okay, so the more traditional way to write this is to put the constant term out in front of pi. So in this case, we would have, when we multiply that out, we're going to have 39 and 69/100 pi centimeters squared. Okay, and remember we talked before about leaving our answers in terms of pi. That gives us an exact, well, I shouldn't have done that. That gives us an exact amount for the area of that circle. That's not an approximation, that's an exact amount because we left it in terms of pi. Okay, what about circumference? Remember, circumference is the distance around the circle. And how much rope would it take? And we're going to call that C. And remember that the formula for circumference is 2 pi times the radius, which in this case is 9.7 millimeters. Okay, so 2 pi times the radius. So we can take the 2 times the 9.7 to have that constant term out front, or constant out front, and that would be 19.4 pi millimeters. Okay, so that's the circumference of that circle. Okay, and again, we left it in terms of pi. That's an exact answer. Okay, so we're going to look at one more exercise here. And if you look at this circle here, each of the squares in the grid to the right here has an area of 1 unit squared. So each of these little squares here that I'm tracing out has an area of 1. Okay, so they're 1 by 1. Estimate the area of the circle shown by counting squares. So I'd encourage you to pause, and you've got this in your notes. So find some way to mark them and count them and see what you come up with. Okay, I had to count it a couple times. I colored in the squares, the ones that were whole, and then combined some of the partials. So when I had one like that, and then one on the other side like that, I called that a whole. These two together, I called a whole, as with these two right here. So by doing that, you should get about 78. That's about what I got, and that's what the answer key shows too. And 78 what? Well, they're square units, or units squared. So we get 78 units squared. just by counting that, and that's just an estimate, of course. Then it says calculate the area of the circle using a radius of 5. So we can use a radius of 5 because if we look here in the center of the circle and count out, we see that is 1, 2, 3, 4, 5 units. So we've got the area is equal to pi times the radius squared, 5 units squared, and we're going to use 3.14 for pi. So our area is going to be now approximately, let's put in our approximation for pi, 3.14 times 5 units squared is 25. So we're going to have times 25 is the 5 times 5. The units times the units is units squared. So when we multiply that all out, and a calculator is good for this, we're going to get 78.5 units squared. Wow, that's pretty close. Okay, we were only off, if you compare these two estimates, just by counting and informally combining, and then here by using 3.14 for pi, 78.5 units squared. So that's a pretty good confirmation that we counted right, and also confirmation of that area formula for a circle. Okay, so our goal for this lesson is to come up with a decimal expansion for pi. And we've said that pi is an irrational number, so we know that it's not going to be a repeating decimal. It's going to be an infinite decimal that doesn't repeat. You know, we might say that 3.14 is the decimal expansion for pi. But that isn't exactly the case. That's an approximation for pi. So pi is approximately 3.14, but it's not complete by any means. So stop for a moment and think about what you would need to do to determine the decimal expansion of pi. Remember, for square roots, we just tried to get closer and closer and closer by multiplying a number by itself. We don't have that ability here for pi, so what could we do? Okay, so just think about it for a minute, maybe talk to somebody about it, and then we'll proceed. Okay, so what is pi? If you look at the circle here, I have a circle and the radius is 1 unit. So the area of that circle here is equal to pi times the radius, which is 1, squared. And the units would be square units here. So the area of this circle is pi units squared. So we could call this, we're going to call this a unit circle because it's a unit circle because the radius is 1 unit. And the area of this circle is just pi. So if we ignore the fact that it's, you know, units squared, even though we know it has to have some kind of units, it's square units, the area of this unit circle is equal to pi. So we can use that. We're going to use that and the counting the counting strategy that we used on exercise C to come up with some closer approximations of pi. We're going to see how close we can get to it, expanding the decimal that way. So in order to do that, you're going to need some grid paper. And it's provided for you. At the end of this lesson, you should have a sheet here with a 10 by 10 grid, and then you're going to have a 20 by 20. But we're going to start with a 10 by 10 grid. If you don't have this sheet, you can just get a piece of graph paper, and what you're going to need to do is mark off a radius of 10 units or 10 squares on your graph paper. Get a compass and draw this circle. Don't try to freehand it because it won't be a perfect circle. If you don't have a compass that large, you could use a string and a pencil. Just hold the string here, and then hold the pencil with the string here, and then swing out this arc. So, however you do it, either use the copy provided or draw your own on graph paper. You want to do this. So this is a quarter circle, right? And a quarter circle is marked on here. So if the area of the whole circle is pi, the area of the quarter circle is equal to pi divided by 4, right? We've just taken it into 4 pieces. So this area here will be pi over 4. Okay, and if we think of this as 1 unit here, which is what we're going to do, this area here will be pi over 4 in the quarter circle there. Okay, so we're going to be estimating pi by this method. So what we want to do is we want to get a lower estimate for pi, something that we know is too low, and a higher estimate for pi, something that we know is too high. Okay, so what we're going to do is we want to count the circles just inside this this semicircle, and then those outside. So I'm going to use I'll use red for inside. And so what I'm going to do is I'm going to trace out all the completely whole squares. Looks like this one. We'll count that one as all the way whole, and come down here. And so I'm just stair-stepping my way down. And I'll take all those. So all of the, if I count up all these whole squares, I know that that's going to be less than the area of this quarter circle, right? So let's use a different color for outside. We'll use blue. Okay, so outside, I'm going to try to block off all the ones that are not whole in this 10 by 10. Here we go. Here. Come down here. And that looks like it's a little... Yeah, that one should count. Here we go. Might be a little too small. Okay, we'll go this way. And here. And what I'm trying to do is just make sure I'm stair-stepping right to the edge of our circle. Okay, let me get just a black. So what we've done is, or maybe not black, we'll do a dark green. So we've got this 10 by 10 area here. Got a 10 by 10 area. So we know that the area of our semicircle is bigger than all of these squares, if I count them together, And it's smaller than if I count all of these inside this blue line and this way. I know that the area of my circle is less than that. So I can sandwich the area between those two numbers. So I've got a lower bound and I've got an upper bound for my circle. Okay, so all that's left to do now is to count those. But before I do that, let's think about, we're calling this a unit circle, which means that this length here is 1. Okay, so from here to here. So each of these, so if this is the unit 1, then this whole square has an area of 1, right? Because it'd be 1 by 1. So each of these little squares would have an area of 1/100th, okay? So each of those squares would be 1/100th of a unit, of a square unit, okay? Because I have 10 by 10, so that's 100 altogether. So that's 1/100th, and these are units squared. All right, so is that clear? So let's count. What is our so we could say that the area, or this pi over 4, let's use purple here. We got pi over 4 is greater than something and less than something. So it's greater than, so what I need to do is count, let's see, let's make that red. Count all these. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And if I keep counting, and you should count on yours too, and you might have gotten slightly different results, that's okay. I'm going to count every one of these. And when I do that, I've already done it. I know that I get, so all of these are whole squares. I get 69 for that. So 69, whoops, check my pen again. 69 hundredths of a unit squared is, I know that number is less than pi over 4, which is the area of that unit quarter circle, right? And if I now add in, so let's do this in blue. Now I'm starting with 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86. So the red plus the blue is 86. So I know that my area is less than 86 hundredths. And these are all units squared. Okay, so I'm going to rewrite that inequality. I have pi over 4 is greater than 69 hundredths, and it's less than 86 hundredths. Okay, and this all goes back to the unit square. Now, what I want to do, so now I can write this as pi over 4 is greater than, I'm going to write these as decimals now, and less than 0.86. Now I want to multiply everything through by 4. And I can do that because of properties of equality, right? So I'm going to multiply this by 4. I'm going to multiply this by 4. And I'm going to multiply that by 4. So that's going to give me a new inequality right here that I know is true. But it's going to have pi in it instead of pi over 4. So 4 times 69 hundredths is 2.76, and 4 times 0.86, or 86 hundredths, is 3.44. All right, so by counting, now does this seem reasonable? what we generally use for pi is 3.14, which is definitely in between these two boundaries. Greater than 2.76 and less than 3.44. Okay, so I could say definitely I've proven that pi has to be between those two numbers by my counting strategy here. Okay, but we could make this quite a bit better, really, even just with this same picture. So let's look at a clean one. If you look, you could see that definitely there were some whole units of, whole squares that should have been counted inside the circle that weren't, right? Like in this area, say like in columns A through B, there's definitely 1, 2, maybe 3 extra whole squares that we could count in addition to the, what do we have, 69 that we started with. So maybe 3 extra. If you look at columns C and D right here, these two, probably there's another one right there. Let's keep going. E and F, these look like 2 halves that were inside the circle, so that'd be another one right there. And then if I look here, maybe column G has another one. And column H, how many more that would be inside? Maybe 1, 2, 3. So 6, 7, 8, 9. 9 more squares added to our 69 that we already had. And we get 78. So what that means is, let's put our pi over 4. We can say that pi over 4 is greater than 78 hundredths and less than, now we had 80, what do we have, 86. But we could do the same thing with the outside of the circle that we did with the inside. So, so if we look here, we didn't count this, we did count this square, and maybe we didn't need to. So we started with 86, and we're going to subtract some. So let's see, in column C, we could subtract 1, and then D and B would be another one. So it'd be -2. And let's see, this one right here probably didn't need to be counted. So there's 1 and these 2 halves, there and there. So that's another 2. You see what I'm doing? I'm just drawing it in a little closer. So maybe we could have counted another one there. So minus another one, that's this one right here. And then if I add this and this and this all together, plus some of this I didn't count up there, I could probably get one more in there. So minus another one. So all of this is 2, 4, 5, 6. I could take 6 off of that. So it was 86 as my upper bound, but I'm saying maybe 80 is a closer estimate, just using this. So we could call this 80. So what does that give us for a better approximation of pi? Okay, we're saying it's between 78 hundredths. Pi over 4 is between 78 hundredths and 80 hundredths. So let's come over here. Pi over 4 is greater than 78 and 80. Okay, I forgot already. 78 hundredths and less than 80 hundredths. Okay, so, and remember we're going to take and multiply each of these by 4 so that we get our estimate. We want our estimate for pi, not pi over 4. So that leaves us with pi. 4 cancels there. And 4 times 78 hundredths, so it's 4 times 0.78 is 3.12. And 4 times 80, 4 times 8 is 32, so this is going to be 3.20. Okay, so now we've got this inequality. So we've got pi sandwiched between 3.12 and 3.2. And we're saying pi is, we've been using 3.14 for it. So we're getting a pretty close estimate just doing this. Okay, but we can even get better because you have another grid. Now, I'm going to just give you the numbers for this. I'm going to let you do it. But can you see how we can get so much closer by doing it with the 20 by 20 grid? Now, with a 20 by 20 grid, we're still saying that the radius of this circle is 1. Okay, so let's trace out the square here. So this is 20, 20 squares by 20 squares. But each of those is 1/20th. So one of these little squares, how many are there altogether? Well, there's 20 times 20, which is 400, right? 20 times 20 is equal to 400. So each of those little squares is 1/400th of a unit squared, okay? Because this whole big square is 1 square unit. So each of these little ones is 1/400th because there's 400 altogether. Okay, so your job now is to count the whole squares that are on the inside bound and then on the outside draw those lines that give us an upper bound and a lower bound. Okay, so pause the video and do that. Remember to use some good counting strategies, like you can, some of these just count in blocks, like so, that you know are all whole squares. So don't go counting one by one. You can knock this out pretty fast. Okay, so go ahead and count inside and outside, only whole squares. Okay. Okay, so all this stuff counts. Okay, so use some time-saving tactics here so that you're not counting all day. And remember to draw the outside bound. Okay. Okay, so here's what your boundary lines might look like, something similar to this. And I'll give you some numbers that were counted. So for this one, we're going to have, again, we've got pi over 4, and we're sandwiching it between these two fractions. So remember, each of these little squares is 1/400th. So I counted 294 inside the red boundary, so 294 over 400. And inside the black, we've got 333 400ths. Okay, so again, we're going to multiply through by 4. So that we get an estimate for pi. instead of an estimate for pi over 4. I don't know if I said this explicitly, but we could have done this with the whole circle. But if you think about it, we're saving a lot of time by just doing 1/4 of the circle, because all of these would be, the other 3/4 of the circle would be exactly the same, right? So that's why we're multiplying by 4 here. So this becomes, notice this time the 4 and the 400 are canceling, so this is just hundredths. So this becomes 2.94 is less than pi. And this becomes 3.33. Okay. And so that's just looking at whole squares. If you refine down to even partial squares, then we can get a better estimate. And so by counting half squares, I get this, but you might get something slightly different. 310 and less than 321. Okay, so as I multiply through by 4 on this, I recognize that those are just hundredths now. So I've got 3.10 less than pi less than 3.21. Okay, so we've got a pretty close estimate here. I actually got a little bit closer even with this, this 3.12. I was cutting it pretty close on this though. So that might have been a little bit cheating, but anyway, here is a pretty darn close approximation for pi, or decimal expansion of pi, just by looking at the squares within this 1/4 of a unit circle. Okay, so I'm only off by 4 hundredths here, and by 3.14 by 14 hundredths up above there. So that's pretty close. Or not 14, I'm sorry, 7 hundredths, because this 3.14 to 3.21 is 7 hundredths. All right, so pretty close. Pretty close guess, 7 hundredths of a unit. Okay. All right, imagine that we do that process a few more times, and we'd have to spend quite a bit of energy doing that. And imagine that we got pi to within this boundary. So we've got 3.14159 and 3.14160. So these are within 1/10,000th. Let's see. Hundreds, thousands, 100,000ths. Okay, within 100,000th for pi. But something interesting happens when we square it. And this is a separate point. This is true for any decimal numbers, especially irrational numbers here. So we've got our approximation for pi, accurate out to out to this digit here, out to the thousandths. Okay, and now, or yeah, this is to the thousandths. This is okay. Sorry, back it up. So we have this estimate for pi here, and we've taken it all the way, whoops, not my pointer. We've taken it all the way out here. We've got, 59 here and 60 here. So we're really just off by 1. in this, let's see, 1, 2, 3, 4, fifth decimal place right here. So if pi is between these two numbers, then pi squared is between this number squared and that number squared. Okay, so think about that for a minute. Make sure you agree. We did this when we were getting the decimal expansion of square roots. Okay, so what I want you to see is what happens when we multiply these numbers that have decimals. So we multiply this number by itself, or square it, and this is the result that we're going to get on a calculator. Okay, and this would be the result of the upper bound. All right, so let's look at the digits here. So they both have a 9 in the ones digit. That's good. They both have an 8 and a 6 and a 9 in the tens, hundreds, thousands. But that's where the similarity ends, right? So after that, this part of the number is all different. Okay, and so what we could say is we have pi squared, we have accurate to, we could say pi squared is approximately 9.869, and that's as far as we can go. Correct to 3 decimal digits there, 4 digits in all. So you lose a little bit when you do that multiplying. So just be careful with that. In the exercises, well, we'll do it together. The exercises that follow, they ask us to make an estimate for the square of a number. So we'll look at that. We'll look at that together. So, okay, so the point of this screen here is just to show you that just because you can put this number in your calculator and it's really, really, really close to what I'm working with, these extra digits are really, for all intents and purposes, meaningless. They're not accurate, okay? Notice they're different on both these numbers here from the original. And so I can see how accurate I can be. I can be accurate out to the 3rd decimal place in this particular situation. Okay, sometime in science you'll learn about significant digits, and that enters into play here quite a bit. So let's look at exercises 1 through 4, and then we'll be ready for the problem set. Okay, Gerald and Sarah are building a wheel with a radius of 6.5 centimeters and are trying to determine the circumference. Gerald says because 6.5 times 2 times 3.14 is equal to 40 and 82 hundredths, the circumference is 40.82 centimeters. Sarah says because 6.5 times 2 times 3.1, so anyway, you can read that, is equal to 40.3, and 6.5 times 2 times 3.21 is equal to 41.73. The circumference is somewhere between those two numbers. Explain the thinking of each student. Okay, so think about what Gerald and Sarah are saying and why are they saying it the way they do. Okay, so Gerald he just used 3.14 for pi, and so he's getting an approximate value for the circumference based on 3.14 for pi. Sarah wants to know what it's between, so she's giving a lower and an upper estimate for the circumference of the wheel. Okay, so both could be useful in different settings. If you just want one number, then you might want to go with Gerald's. If you want a range, you could go with Sarah's. Okay, so that's what they're thinking there. All right, so let's look at number 2. Estimate the value of the irrational number 6.12486 ... squared. And we want to see what this is accurate to. So I'm going to give myself a little bit more room here. Okay, so my number is 6.1248 and I know there's digits that follow. So I know that my actual number, well, that's right there. This one, this number here is greater than something and less than something, right? So it's greater than 6.1248 because that just, chops off all the rest of the infinite digits, right? So I know my number is greater than that, and I know that it's less than 6.1247, right? Because if I put a 7 in this spot here after the 8, all the stuff that comes after it, no matter how infinite that decimal is, will never add up to an extra 1 in this place value. That's just the way our place value system works, right? So I know that this number here is sandwiched between these two. So even though it's an infinite repeating decimal, I know that it's between these two numbers. So because I know that, if I want to estimate the square of this infinite repeating decimal, then I know that it's between the square of these other two numbers. Okay. All right, so definitely you're using a calculator for this. I'm going to write out a lot of digits here. If I square this number, let's go back to purple, I get okay, I don't want you to have to sit there and watch me write it. So if I take this number and square it, I get this with all these decimal places. Okay, and here's my number. This is actually I shouldn't have written it this way. This is actually the repeating decimal here. It has extra stuff on it here, and it's squared. And I know that it's less than, this number squared, which is right here. All right, so I want to know, how accurate can I be when I square this repeating decimal, given those digits? Well, so let's look at what they have in common. 3751, 37.51. Once I go past there, then I'm getting differences. All this part of it is slightly different. So I know that this number squared is, I can get it accurate to the hundredths digit, 37 and 51 hundredths. Okay, I don't want to go through these last two in the video. You have the teacher's notes. You can check these. But this next one in number 3, if I square this, I'm going to, the lower bound for this number is 9.204107, truncated like that. So then my number, my square that I'm trying to find, and so that's going to be between that and the next place value up, right? 204,108. And so these numbers squared. So the number I'm trying to find, that goes right there. And so this one, because I have a few extra digits here, this one is going to be correct out to the third decimal place. So this is going to be correct to 84 and 715 thousandths. All right, so you can punch those out on your calculator and see where they are. So this is, this is interesting, and this is why in science I'm always telling you don't need to carry all those digits because they're not accurate anyway. Okay, this next one, because I have even more digits here, this one's going to be correct to 4 decimal digits, and it's going to be approximately 16.1148. Okay, so I can get that out to 4 decimal digits. Okay, so what did we talk about here? We talked about the fact that irrational numbers need to be approximated in order to do any computation with them. So we can't just leave it as pi. We can leave it as pi as long as it's useful, but if we actually need the number, we need to approximate it. So commonly used and really good approximations are 3.14 and 22/7. If you want to use a fraction, 22/7 is a really good approximation, but it's still an approximation. And also the other thing we looked at is that when you use an approximate value of an irrational number, it produces an answer that is accurate only to the first few decimal digits. So you're going to want to round your numbers off to the hundredths usually when you're using 3.14 for pi. Okay, so good luck with the problem set. Check your answers as you go to make sure you're, you're getting it. And we'll see you back here. Oh, mid-module assessment comes after this lesson. So you should do that just to see what you might need to review or how you're doing on that. So good luck with that, and then we'll be back here for lesson 15. We're going to start a section on the Pythagorean theorem.